In an earlier video, we have seen the prediction methods associated with reinforcement learning, and more specifically, we saw both Monte Carlo and how the temporal difference method manages to reduce the Monte Carlo variance, at the same time picking up an increased bias relative to pure Monte Carlo kind of methods, and also providing us the advantage of online learning. Now, to learn an optimal policy, we'll continue to engage what we have seen in the MDP videos as what an algorithm is actually called policy iteration. And we will be generalizing it in the following sense. In the MDP discussion, we have been working towards evaluation of a value function, either the V or the Q. And then after we evaluated the function, we were determining with a greedy step an optimal policy and gradually. So we will basically alternating between an evaluation and an improvement step. And then ultimately we have seen that this is a contraction, and this actually led us to a convergence towards an optimal policy. Over here, what we will do is we will generalize that kind of policy iteration in a couple of things which I want to write down. So in GPI, that covers a whole range of reinforcement learning kind of algorithms. Instead of let's represent this kind of contraction towards the sort of other Q star or the pi star, the optimal kind of policy and the optimal kind of value function that we are interested in. Instead of actually starting from some kind of initial Q value and some kind of a policy, and we always kind of strive to sort of estimate a Q function and then use this kind of Q function to greedily form, if you like, a policy. So this is basically my Q1 for the first iteration. That's kind of my pi 1, Q2 and pi 2, something that we have seen in policy iteration and gradually kind of converging into the optimal value function, the optimal kind of policy. What we will actually be happening over here is that we will take incomplete steps. So we will generalize the policy iteration to allow us to take incomplete steps towards its goal, which the goal is the estimate of the value function and the kind of policy. So this means that we actually will see that we may be starting from, let's say, some kind of a policy over here and work ourselves towards, if you like, a value function, but this value function may not necessarily be on that kind of trajectory, and then take kind of greedy steps to go back to some kind of policy and so on, but still be able to converge as we go towards, if you like, the sort of final determination of the value function and the optimal kind of policy. So this kind of a generalization will, and the proof that this converges is basically what GPI is actually will do for us. And as we'll see, the algorithms that we will be dealing with, which will be called model-free control, come under that kind of umbrella. So another key distinguishing attribute of various kind of model-free control algorithms is whether or not they're working with the so-called on-policy assumption. And in the on-policy assumption is that we have the same policy transitioning the environment and learning how to control optimally the agent. So this is the typical letter that we have used pi for this kind of policy. And to contrast that, we have the so-called off-policy methods, where we have different policy to transition the environment and therefore generate trajectories, sort of episodes, etc. This policy will be called behavioral policy and will be symbolized by mu. So we have a different policy to transition the environment and from the policy we learn to act, and this will be actually be called the target policy. Pi. The reason we actually have these two type of algorithms, control algorithms, is that in many instances we actually have found that sort of off-policy methods can offer an advantage compared to on-policy methods. And they are being extensively used when we, let's say, would like to mimic a certain behavior that we see from another agent, when we actually have the requirement to explore far more in the environment than what potentially the target policy allows us. So by differentiating between two different policies, the behavioral policy that generates experiences and the target policy, we're actually able to satisfy both of those requirements. So the first method we will actually see under model-free control is called epsilon greedy Monte Carlo control. And despite its kind of complicated name, it ends up being a direct extension of what we have seen first, the Monte Carlo estimation method, coupled with a greedy policy, but this greedy policy has a kind of twist. So as a kind of reminder, in that video on when we discussed Monte Carlo estimation of the value function, we have focused our attention to estimating the state value function. And the state value function was updated on a per episode basis because only at the end of this episode we had the quantity which we actually needed for the estimation of the state value function, which was basically the actual return, the GT as we actually call it over here. Now, there is going to be a problem with applying a control policy, because at the end of the day, we cannot take a greedy step when we have state, because at the end of the day, we need an action state value function. We need a Q function in order to actually apply any control policy. Only when we know an estimate of the Q function that basically conveys the information as to how viable an action we have taken at a specific state is, only then we can apply a control policy. Okay, so what we can actually go back to this section we're discussing. So this is the reason why we need to apply a greedy step. However, at the same time, if we are applying a greedy step on actions out of the same policy, if this kind of policy is deterministic, you may actually understand that the actions we are selecting at every moment, at every state, is going to be one and the same for no matter how much kind of experience we're generating. So there is an exploration issue that we are trying to solve with this twist, if you like, on that kind of greedy step. So we can definitely take a greedy step, but what we will do is we will modify slightly the greedy step to introduce some form of randomization. So they introduce, if you like, a constant, like you can imagine it as being kind of a coin tossing that we do for every greedy step when with a coin which is bent with bias epsilon, and every time that it is the probability of so epsilon is the probability of coming up with heads, and 1 minus epsilon is obviously the probability of coming up with tails. So every time that we take the comes up with heads, then we are do not follow the greedy policy, and we are selecting an action out of the remaining actions so that we have available at every state. So we are effectively randomizing that kind of action selection with a probability of epsilon. And when we have 1 minus epsilon, in other words, when we have tails, then we are following the greedy action, and we are selecting, if you like, the action that corresponds, in other words, to the maximum possible Q functions out of the ones that we have available to us. So that is, in broad terms, what the greedy approach is, and what is actually that second step, as I mentioned, that policy improvement step is actually giving us more exploration as we go along. So we have given us opportunities to see more diverse set of experiences, although it is going to be a compromise. That's something that we will solve a bit later with another approach actually called SARSA. And in that approach, it will actually be, we actually going to recover both the benefits of the Monte Carlo and the temporal difference methods. So this is the, however, before we go there, this is the flow of the epsilon greedy Monte Carlo. So we are effectively generating the episode just like we have been doing in any Monte Carlo method. We are for each step of the episode, we are computing the return. And so we append the returns and to calculate, if you like, the average of the return. So this is basically the Q function, and this is the corresponding kind of backup tree for estimating the Q function that we have seen before. And over here, we are determining, if you like, the optimal action. But before we taking this action, before we actually setting up the policy based on this maximum action, we are flipping a coin. And if it is epsilon, we are randomizing the action. And when it's -1 minus epsilon, then we are indeed taking the A star, the optimal kind of action. So this is the gist of the algorithm. It consists of estimation step that follows, if you like, the Monte Carlo prediction step that we have seen earlier, and a slightly different greedy step for policy improvement to effectively implement what we call generalized policy iteration. And the interesting thing is that this algorithm also has been shown to converge to an optimal policy. So closing the discussion on the kind of model-free control, we will see SARSA, which is one of the most important kind of reinforcement learning algorithms that actually naturally flows out of this epsilon greedy Monte Carlo. And if I may kind of start the discussion, SARSA will involve two steps. We'll marry the temporal difference method, estimation or prediction, of the Q function. So that's the first thing. And then, of course, the second will maintains the epsilon greedy policy improvement. So in all, we are still in this generalized policy iteration kind of umbrella of algorithms. And in the Monte Carlo approach that we have seen before, we have been kind of generating kind of episodes. We were estimating, if you like, this value function, the Q function, over many episodes, keeping tab of the states and actions that we've been selecting for the policy that we wanted to evaluate. Over here, we will migrate into the temporal difference for all the advantages we have listed in the temporal difference prediction video discussion. And for those who have not seen that kind of video, I suggest you go and watch it. And effectively, the tree that we will be forming, the update tree for updating the Q function and therefore estimating it, is going to start from, let's say, a state that we have been and taking an action A. So this is basically the action. Before we were in some kind of a state S. So let me just start with a state then. Start with a state S, taking an action, committing to an action A. Obviously, we are going to be migrating into another state, S prime, after and at the same time receiving a reward R. And at this new state, we are taking an action A prime. So what we will effectively do here is to, for this specific S comma A Q function, we will be using this Q function for S prime A prime to update it. And we'll see now how, using exactly the same formula we have seen in the TD prediction. And that formula is as follows. This is a Q of ST AT is equal to Q of ST AT plus alpha RT plus 1 plus gamma Q of ST plus 1 comma A T plus 1 minus Q of ST AT. And this is basically what we call the TD target. And that's basically the such a kind of update, which kind of naturally flows as given the TD discussion, the temporal difference discussion we had. So effectively, the state action value function or Q function is updated from the earlier one, the earlier value it has by alpha, which is a small number, in the direction of the so-called TD error. And that's the TD error, the difference, in other words, between the Q function that we have in memory and the so-called TD target, which is effectively the it is really the backup given the state ST plus 1 that we call here S prime. So S prime is the sort of ST plus 1. In fact, we have been writing it in a kind of a reverse way. So this is ST plus 1 is equal to S prime. AT plus 1 is equal to A prime. And here we have ST is equal to S and AT is equal to A. Okay, so that is the SARSA update. So the second, the maintaining, if you like, the epsilon greedy policy, I'm going to write it here with words. So this is basically an on policy. We only have one policy here, pi. So we continue to estimate Q of S comma A. And at the same time, change via the epsilon greedy policy improvement the pi. Okay, so this is in the side you actually can see the general form of this kind of algorithm. And let me take you to that site now. So this is the general form. It's worth noting that the sort of convergence, and this is basically a good example of why we kind of introduce the generalization in this kind of policy improvement. Notice with the original kind of algorithm of policy improvement, we were always been hitting this upper line that kind of represents, if you like, a constraint in terms of the sort of like in sort of optimization, linear programming and so on. We see these kind of lines as constraints. And so we never hit that because with the policy improvement, with the estimate over here, we are doing the estimate online. As every experience that goes by, we are doing an update. And therefore the epsilon greedy improvement over here is actually happening from that update that we are doing in the previous time step. So every single time step there is an opportunity for update, and therefore an opportunity for doing this epsilon greedy improvement. That's why we actually call SARSA an online algorithm. And this is basically the pseudocode for that. So we initialize the Q table. This is a table with states and actions. And we choose, so we initialize, we pick up a starting state, and we are choosing, if you like, an action from S using whatever policy we are initializing it with. And we are repeating this. This is basically for each step of the episode. We are doing that, and of course we are updating the Q function over many episodes. Okay. So this is basically what we just discussed. That's the Q function update, and the A prime here is selected out of the policy improvement. Okay, so what the TD target accommodates that kind of policy improvement step, includes that kind of policy improvement step. All right, so this is basically the SARSA kind of algorithm, and I think it's worthwhile now looking at an example where we, in Python, where we will basically see an implementation for a specific environment that we have brought here. So if you go to the course, the repository of the course site, you actually will see here under SARSA a directory called GridWorld, and one subdirectory called environment, plus the main driver program, which is a Python notebook. And this environment that you see here will actually involve a grid world of 5x5 cells. And in this grid world, we have all possible actors, up, down, left, and right. We will be exercising, obviously, the SARSA algorithm that we just discussed. And the build canvas effectively builds this image over here, this canvas where the agent is located, and there are certain rewards, negative rewards and a positive reward on these specific cells. Of course, you can programmatically kind of set the rewards at any cell you want. Then we have the usual kind of functions, like the step function. So this is the most important function, the step function, that it is taking an action and transitions the environment into a new cell. and this is effectively the code for that. It is not necessarily a stochastic environment, so you can actually see that it is transitioning kind of the environment deterministically. There is also in the step function there we will be getting the next state. Okay, so that's the next state, and the reward. The reward is going to be defined over here, and that's basically it. You will have, if you like, these two, S prime and R, coming out of the step function. That is really the environment. It's a very simple environment. And then, of course, we have the agent. This agent is the algorithm itself, some parameterizations of the SARSA agent. This is going to have an alpha of 0.01. This is alpha was met in the Q function update equation, a discount factor gamma of 0.9 and an epsilon of 0.1. Epsilon was used for the epsilon greedy policy improvement. Then we have a Q table that evidently consists of 4 tables, one for this action, for each action up, down, left, right. Okay, so there is a method called learn. So in this method, we are sampling from the environment. So we have the sort of SARSA coming in as arguments, and what we produce at the output is we're updating the Q function. So we're updating the Q function, and we have then after that we have some other methods like the get action. The get action here is as we discussed during the policy improvement, we will have some form of randomization based on the biased coin that has a crossover probability with epsilon, and therefore we are taking a random action every time that we are within epsilon, and after 1 minus epsilon is where we're actually taking the best action out of the existing table. Okay, out of the existing Q table. Okay, so that's basically that's the greedy step. So that's the randomized step, epsilon, and that's the whole thing is called epsilon greedy. All right, so that's basically it. The main routine is instantiating the agent. It starts with episode, creating episodes. So let's say 1,000 episodes. We are starting from a reset function of the environment, and we also get our first action. So the reset function in the environment gives us an initial state that we can start the process, and we are taking an action based on the get action method that we just saw. And then we have an infinite loop that we will break every time that there is a new, the existing episode kind of ends, and then we go into the next episode and so on. So during the episode, we are rendering, so we will see that we're able to, trigger the environment. So if we just run it, you will see that the window will actually pop up with the agent moving and acting in that kind of environment per the SARSA function, and of course the SARSA kind of control policy. So we have the step function, the get action, and the learn method, as we have seen from earlier in the agent. So these are from the environment, and then the agent determines the next action and of course updates the Q function based on that, and then the whole process kind of repeats according to the temporal difference kind of method in terms of state estimation.